Okay, now we will look at the solutions for the assessment in author. So this is the first question in your author. So you have a proton, the charge is equals to 5 nanocoulombs and it is moving with a speed of 1 times 10 power 6 through a magnetic field with magnetic flux density B equals to 5 Tesla. It experiences a magnetic force of amplitude 0.014. So what is the angle between the magnetic field and the moving direction of the proton? So this question involves the force, okay, which is experienced by a charge when it is exposed to a magnetic field. So in this question you have to apply, okay, this formula. Okay, this is the formula where it involves the value of the charge, okay, the velocity, and also the value of the magnetic flux density. And the question is asking you the angle, okay, the angle by giving you the force, giving you the Q, giving you the U and B. They want you to find the angle between the U and also the B. So basically we will apply these equations. So we can look at the solutions. Okay, this one. So you have the Q, you have the U, B, and also the F. Okay, so you have to apply these equations. This equation is a cross product between two vector quantity, so we can rewrite it to be this one. Okay, so we just fill in the blank, okay, all the value that we know, and sine theta is something that we don't know. Okay, so by simplify all these things, we will get our angle equals to 34.06. So this question entitled 3 marks. Okay, so we will look at the second question. This is your second question. You have 2 ampere of current element flows from this point to this point. Okay, it is placed in an environment which contains magnetic field flux density B. So you have to predict the directions and also the magnitude of the force exerted on this current filament. So this is a question involve the force on a current element in an external field. Okay, so you have been given the I, okay, you've been given the B, so you have to find the force. Okay, now you have to perform integration with respect to the length of the current element. So the question gives you the starting point and also the ending point of the current element. So let's look at the solution. Okay, it is from 0, 3, 0 up to 0, 3, 10. Okay, so the current filament flow in these directions, and the B is in the Y directions. Okay, so I has been given 2 ampere. Okay, and DL represent the length of the current element, okay, which is in the Z axis along the Z directions. So here is dz. Okay, so here I put it positive Z. Okay, and I integrate it from 0 to 10, follow the direction of the current flow, 0 to 10, okay, and B is equals to 10 in the Y directions. Okay, so perform integration as usual, you get this thing, and ZY you will get negative X. Okay, when you cross product Z and Y, you will get negative X. As a result, you will get your force equals to negative 200 X. Okay, in the X direction, Newton. Let's move on to the third question. So this is your third question, very similar to this one. I have explained this thing in the lecture video. Okay, we will look at this one. You have 2 infinite length of wires. They are located as shown in the figure here. So you have to determine the force per unit length. Okay, which means that it is F over L on both of the wires. Okay, this is I1 15, I2 2 milli, and this is the location. Okay, this point is 3 0 0. Okay, it means that the distance between these 2 current elements is 3 units. Okay, so we will look at the solutions. Okay, so we need to find the force on each of the I1 and also the I2. Okay, so first of all, I want to find the B1. So B1 is the magnetic flux density generated by I1. Okay, so this is the formula. So if you remember what you have learned previously, okay, something like this. So you have to find the magnetic flux density first, okay, and this magnetic flux density is from the Ampere's law. Okay, so look at the solutions. Okay, this is the I, okay, and dl cross product with the unit vector r. So this is the point you want to know is magnetic flux density. So the vector r is pointing from here towards these directions. Okay, this is your direction of vector r from here to here. So it is in the positive x directions. Okay, positive x here. And look here, dl. dl represents the length of the current filament, which is in the negative y directions, negative y. And the distance, like I mentioned just now, between them is 3 units. So this is 1 micro, okay, Tesla or Weber per meter square in the z directions. Okay, yx you get negative z, so you have a negative here. Okay, you get z here. So this is the magnetic flux density produced by I1. Next, I calculate the magnetic flux density produced by I2. Okay, so this is your I2, and you want to know the magnetic flux density at this point. So your vector r is pointing in this way, okay, from here to here. So it is in the negative x directions, negative x. And the current flow in the positive y directions. And the current I2 is equals to 2 milliampere. So you calculate, okay, your B2 will be 1.33 times 10 power negative 10. Okay, in the z directions. Okay, you have calculated the magnetic flux density at each position. Now we want to find the force which is experienced by I1. So in this case, the I1 is exposed to B2, right? So your I1 value is 15. Okay, so here I specify the length is from 0 up to L. Okay, and I specify the direction of my current, okay, is negative y. So it depends on you. You want to specify the direction here or here. It depends on you. Okay, in this case I specify the direction of my current flow here, negative y. Okay, and this is the answer that I calculate just now, B2. Okay, so I will get this thing. Okay, yz you will get x. Okay, but you have a negative here, so here you get a negative. Okay, and look at here, this is F1 over L. Okay, so I will divide the L here, so that's why you didn't see the L here. Okay, so let's move on to F2. F2 is the force experienced by I2, and this I2 is placed in an environment that has a magnetic flux density which is produced by I1. Okay, so I plug in my B1, and this is my I2, 2 milli, and the length is from 0 up to L. The direction of the current flow for I2, okay, here I2 is in the positive y directions, positive y. Okay, so if I continue integrations, I will get 2 nL, 2 nano, and this is the length of the current filament, and moving in the x directions. Okay, when I divide or find the force per unit length, the L here will disappear because I divide the L. Okay, here I divide the L. Okay, so all these represent the mark allocations. You can check after I mark it.